Okay, thank you for the introduction, and thanks to the organizers for organizing this and having me. My name is Deni. I'm going to talk to you about change action derivatives in persistent homology today. This is joint work with Christine Bauer as part of an NSERC USRA from last summer. Well, let me do that. Okay, click. So here's the outline. I'm going to tell you a little bit about what change actions are and what derivatives mean with respect to them, and cover a couple of useful examples. I'm going to talk about a functorial calculus of finite differences that we're then going to use when we talk about multi-parameter persistent homology. So all of this was kind of started with me in 2019 reading a paper by McCleary and Patel called Multi-Parameter Persistent Homology, where they tried to generalize these things called barcodes, and then listening to a talk by Patel at the CMS Winter 2019 meeting, where he described their generalization as, or he thought of it as a derivative of some sort. So Christine and I wanted to find how we could contextualize this in terms of Cartesian differential categories, which didn't quite work. So we looked for Cartesian difference categories instead, and I'll tell you about how that worked out. So a change action in a Cartesian monoidal category X is 5 things. Well, it's really 2 things. It's an object A and a monoid delta A with plus A and 0A as the multiplication in unit, and that monoid acts on the object A on the right by this O plus. We should think about delta A as being an object of changes that you're applying to things in A, if these are sets. So if A and B are change actions in X, a derivative of a map between the objects A and B is a map from the product A times delta A to delta B. So you should think about this as kind of taking something in A and a change that you're going to apply to it and giving you like a change in the image of the function that corresponds to that. And 2 axioms are required to hold. So if we think of X as an element of A and Y and Z as changes to apply to it, the first axiom is that this diagram commutes. And if you loosen the notation a little bit, you can think of this as like a linear approximation for the function f, or the map f, rather. And the other axiom is these 2 diagrams have to commute. And if you do the same thing with the notation, you should think about this as the derivative is almost linear, but there's this action here in the second component. And if you don't change anything, there should be no change in the image. So this is kind of like the derivative of a constant is 0. So some examples: monoids act on themselves by their multiplication, of course. You can also take an object in a monoidal category and in a Cartesian monoidal category rather, and take a product with a monoid in there, and you can have that monoid act on the product by just acting in that component. We're going to be interested in this when you take the monoid to be an op. We're going to take a product with a poset in cat. Abelian groups are monoids. They also have inverses though, so you get 2 change actions there with addition and subtraction. And this is kind of where the calculus of finite differences comes from. This is talked about in section 5.2 of a paper by Alvarez, Pacallo, and Lemay called Cartesian difference categories. And they show there that every function between the underlying sets of abelian groups is differentiable in set. This leads us to a functorial version of this. So cat is Cartesian. You can take an abelian group G and let bold G be the single object category, whose morphisms are the elements, or your composition is the group operation, and so on. And then look at its arrow category. So now your objects in bold G1 are the elements of G, and the morphisms are pairs of elements that make commuting squares in the single object category. So the arrow category inherits addition and subtraction change action structures from G and set. And I'll sketch out how this is done. So the unit is going to be picking out, the 0, like the unit of the group, of course. And the identity arrow is picking out the pair of identities as well. And you can define two functors, plus and minus, by just kind of taking these point-wise sums and differences. So here's a functorial version of that calculus of finite differences. If you have a category with a change action structure in cat, then any functor into the arrow category of an abelian group is differentiable with respect to these change action structures. And how you would define its derivative would be pretty much just point-wise how you would define it for sets. You would take differences. These derivatives are meant to model like finite differences. So you don't have to worry too much about what this is saying. This is more for completeness, but you should notice that here we're really taking these kind of point-wise differences everywhere. And the change action derivative axioms hold because they hold in set, and we're just kind of applying them point-wise. So now let's talk a little bit about persistent homology. So classically, one would study nested sequences of geometric realizations of simplicial complexes parameterized by real numbers. So if you have x less than or equal to y real numbers, then the simplicial complex associated to x would include into the simplicial complex associated to y, and these would be like simplicial maps. You'd compute their homology at each time, and you get a parametrization of their homology groups. And then if you impose some finiteness conditions and you pick your coefficients carefully, then you get a complete invariant called a barcode or a persistence diagram. And from these, you can kind of read off the lifespans of topological features in that filtration. So like, when do holes appear as you're building these spaces up, and when do they get filled in? When are they boundaries of higher cells? And for more reference on this, Zamrodian and Carlson have a paper called Computing Persistent Homology. In section 3, they go over exactly how this is done. So for multi-parameter persistent homology or multi-persistence, you want to study nested sequences of simplicial complexes parameterized by, there should be an n up here, by Rn, not just R. So for each point T in Rn, you'd get you can compute homology groups, and then you get parameterizations of them, but they're no longer linear. So what's the generalization for persistence diagrams and barcodes? What are lifespans? Are they like regions of Rn in this case? So McCleary and Patel had a good way of talking about this, which I'll kind of go over. With the finiteness conditions, you're really looking at functors from a finite lattice L into chain complexes of an abelian category. And the image on all the arrows in L are monomorphisms. So for each point in your lattice, you get a chain complex. You can look at the cycles of that chain complex, which we'll call ZFN, just as McCleary and Patel did. And you can also talk about the boundaries, or n+1 boundaries at that point too, which will denote BFN. Because this lattice is finite, you have a total complex, which is going to be called F infinity, and you have a kind of total cycle subobject, which will denote ZF infinity. So if you want to know about lifespans of these features, you want to know, when do cycles appear? So when are they in this kernel? And then when do they die? When are they boundaries? To do that, you might take a pullback over the total cycle subobject. So here, this pullback would be the intersection of these, and you can think about this as the cycles that appear by the point X, and then by the point Y, their boundaries. So if you wanted to figure out like lifespans for a given feature, you'd have to compute this for every single point. And then you'd have to find a way of kind of cross-referencing all of that information, which may not be nice. And these lattices can get really big if you're thinking about this being applied to data sets or anything. So this isn't a great way. Instead, we'll try to extend these to open sets of a topology. So for any poset P, you can give it a topology generated by these upper sets where you take a point X and you look at all the things bigger than or equal to it. And if we're doing this for a finite lattice to start with, all of these open sets are finite. So we can extend these these cycle and boundary subobjects to open sets by taking finitely many pullbacks. And this is functorial. It gives you a functor out of the open lattice into subobjects of your total cycle subobject. And again, you can take a pullback to ask what are all the things that are born by one open set and which die by another open set, things being n cycles in this case. And you can do this for any two open sets. They don't have to be comparable with respect to set inclusion or anything. But if you want to look at lifespans for something to die, it kind of has to be born first, right? So we really care about this when U is contained in V. Or sorry, U contains V as a set. So this lets you talk about this pullback as a functor from the arrow category of that open lattice into subobjects of your total cycle subobject. So this is how McCleary and Patel did this more or less. And I was reading initially, multi-parameter persistent homology. Their latest version of this is titled Positivity of Multi-Parameter Persistence Diagrams and Bottleneck Stability. And going between those two, they changed some stuff. So they always define persistence diagrams as Mobius inversions of the rank of that birth-death subobject, that pullback that we just talked about. And then in proposition 5.3 for both of these papers, they show this is isomorphic to the rank of a certain quotient object. And this proof uses some kind of inclusion-exclusion principle, which in the original version didn't hold. The reason it didn't hold in that version was because, as I see it anyways, subobject lattices in abelian categories aren't distributive. So it works, but you need to kind of assume that every element in the arrow category, or every object in here, I guess, there's still elements, it's a poset, has at most two maximal proper subobjects. Then it kind of holds trivially because it's distributive for simple reasons. So to fix this problem from the first paper, what they did in their latest version was change the way they defined upsets, which kind of forced this condition. This doesn't seem natural to me with the product partial order on Rn, so I wanted to see if there was a way to kind of retain their original result. And the way that I was thinking about doing that, or Christine and I were, the rank of that quotient object, which I haven't told you about yet, but I will show you eventually, makes sense as a discrete derivative if I just read it. And to me, it sounds like the Mobius inversion is like a computational tool that can be used to compute it when you have particularly nice lattice that you're working with. So the way that we formalize this is we want to see it as a change action derivative of some extension of that birth-death subobject functor. And we're going to use the examples above and that functorial calculus of finite differences to do that. And the reason that we wanted to do this in the first place was I was learning category theory at the time, and I thought this stuff makes sense. It'd be nice if I could learn about TDA more in this language. And it seemed like categorical differentiation could be a useful perspective for people who like to program and actually compute this stuff. So how do we extend this birth-death subobject functor? For a post set P, you can take any point in there and you can let little c0 be the set containing that point. And then you can inductively define little cn. First, C1 would be all of the maximal proper subobjects of X, the point you started with. C2 would be all of the things that are maximal proper subobjects of those, and so on. And then define big Cn to just include the element X that you started with so that you know where you came from. Because if you do this process from two different points, you can get the same thing. But you want to know where you started with, where you started from, rather. Then the collection of all of these big Cn's for each natural number n and for each point in the post set P is a partially ordered set. And it's ordered pretty much exactly how P times n op is ordered. That is, there's an inclusion from the set of all those to P times n op. And we care about when P is the arrow category of that open lattice. So for that case, you can extend the birth-death subobject functor using subobject unions by taking a pair of open sets U containing V and a natural number N and mapping it to the union of all of the birth-death subobjects for the things in the nth kind of step backwards. I've been calling these covers because they're maximal proper subobjects. I think Johnston called them that as well. And because of the way the partial order is defined, you get an inclusion of these unions when you have an arrow like this. Okay, so now we want to extend the rank function. If we let GA be the growth in D group of the abelian category A, and let frag R be the rank function for any monomorphism, we have A to B, we have that the rank of A plus the rank of the co-kernel object is equal to the rank of B. So this gives you a functor from any of these sub-object lattices in A to the arrow category of the growth in D group by sending a monomorphism here to this commuting square in the single object category. So look at the composite of this union thing, this union functor and this extended rank functor. This thing, this is a functor from tau1 op times n op into the arrow category of the growth in D group. This has a change action structure because it's an abelian group, as we saw before, and so does this because n op is a monoid. So by functorial calculus of finite differences, this thing's differentiable when we view it in cat. We can view all of these things in cat. We can call its derivative bold gamma sub D. Here D is just specifying which cycles we're looking at. So here's an explicit definition of this. Don't worry too much about what's written here. The point is bold gamma is defined by taking all these differences of the original functor, which was this bold ZB. And the way that you can recover the rank of the quotient object that McCleary and Patel talk about is by including tau1 op into this domain by kind of picking an open set and the first set of covers, the things that came just before it. So that's what this is telling you. So then for any open sets U containing V, we have, when we post-compose that last inclusion with bold gamma D, this is going to be gamma D of this thing by definition, which is this difference of the bold ZB FD functor. Here we have C0 of UV, which is just really the set containing UV. And here we have C1 of UV, which is all the things that came before it. And the way that this bold ZB is defined is it's the rank of that union thing. So the union here, you just have ZBFD of UV. And here you're taking the union over all of the things that came just before it. And this is the rank of this quotient. This is what McCleary and Patel showed was isomorphic or equal to their persistence diagram definition. And if you read what this is telling you all of the cycles that are born by the open set U, that die by the open set V, or they become boundaries by V, but they don't do so at any point before that. So it's really the cycles that are born at V and become boundaries, or sorry, born at U and become boundaries at V. So in that sense, we should be able to think of like U set minus V as kind of their lifespan. So here's a summary of all of what I just said. You start with this birth-death functor, you extend it to this union of things in covers. You post-compose with rank. That is differentiable by calculus of finite differences. And then you can recover that, the rank of that quotient by including an open set. And how does this compare to the classical case? Well, if you consider your abelian category to be like vector spaces over some field K, and your lattice to be a finite subset of the real numbers, and if you suppose that F is coming from like a filtration of simplicial complexes, then your upper sets are intervals that are closed on the left and then infinite on the right. An inclusion of them can be thought of as an interval that's closed on the left and opened on the right. And then the rank of that quotient is really the number of d-dimensional holes in the filtration whose lifespan is this interval. So if you wanted to reconstruct the barcode for one of these things, then you would just look at this for all of your open sets, and you could add them whenever you get something non-zero, and the multiplicity would be determined exactly by that value. So that's pretty much what we did. And then haven't really touched that since last fall because I started coming to Dalhousie and doing my master's. But questions for the future include whether there's a Cartesian difference category that these naturally fit into, whether you can define the support of this thing, gamma D, as a generalized persistence diagram, and if it's stable with respect to perturbations. And then also, is it necessary to use abelian groups or the rank function? Could you swap an abelian category for something with enough exactness properties, but nicer subobject lattices maybe? Or maybe do away with that entirely and just look at filtrations of simplicial sets and try to do things in set where you do have distributivity and you can use a kind of inclusion-exclusion principle. And there are some references. So that's all I got.
Great, thank you, Deni.